Good morning, good afternoon, and good evening to everyone joining us live or watching the session later at your convenience. A heartfelt welcome to all the students, faculty, and alumni of BESU, now IIESTShibpur. I am Debojit Cole, a third-year student from Department of Civil Engineering, and I truly honored to be your host for today's exciting webinar. This session is brought to you by the Computer Science and Data Science Special Interest Group as a part of the IIST Alumni Network Program, a GAABESU initiative, where we reconnect the brilliant minds shaped by our institute. So before we begin, I encourage everyone to post your question in the Zoom chat. After addressing the pre-collected question from our student, I will pick few live questions from the chat if permits. So now let's introduce our speaker for the today's session, Dr. Sagnik Nath. Dr. Nath is currently an assistant professor at the University of California. His work focuses on engineering education research, VLSI design, and computer architecture. He completed his PhD from Rensselaer Polytechnic Institute, has published extensively in leading IEEE journals and conferences, especially in superconducting electronics and AI in education. He is also an accomplished alumnus of Electronics and Telecommunication Engineering Department, class of 2015 from our very own institute. Dr. Nath is passionate about using cutting-edge technology to improve learning and teaching experience in engineering. So now let's begin today's session titled Beyond Code, Evaluating ChatGPT, Gemini, Claude, and Maity as AI tutors in computer science and engineering education. Over to you, Dr. Nath.
Thank you, Shubhajit, for organizing and coordinating the logistics of the session. And thank you, GAABESU, for organizing the overall talk, and especially to Shopanda for inviting me to this special session. Let me quickly set my timer to 40 minutes so that I do not go beyond the limit. There we go. So yes, so let me now share my slides. Mhm. So, good morning and good night, everyone. It is a great pleasure to be beginning this talk. And it's always a great pleasure to be revisiting my alma mater, IIESTShibpur, even though it is in virtual, but nevertheless a great honor. So, today my topic of my discussion is this idea that I initially sort of presented at the IEEE Frontiers in Education conference last year. And the title is Evaluating ChatGPT, Gemini, Claude, and Meta AI as AI Tutors in Computer Science and Engineering. So this talk, the authors were me from the Department of Computer Science and Engineering and University of California, Santa Cruz, and my colleague Su Yun Yoon, who is in the Department of Engineering and Computing Education. And so she's a professor over there at the University of Cincinnati. So without further ado, I will now begin. So what I would want to do first is that even though this is meant to treat the assessment of these chatbots in terms of the reliability and accuracy for general students of engineering, before I do that, I want to talk a bit more about the actual context of how we actually got to this specific spot of using AI in today's world, right? So, I think even just few 8 7 8 years ago, none of us could have comprehended this revolution that ChatGPT specifically introduced into our modern day world, right? It's like a huge trailblazer. But how did we actually get here? So I think we need to spend some time talking about the underlying context, right? And that's another keyword, context, which you will hear me mention quite often in this talk. So I want to dive a little deeper into the context of this overall history of how we arrived at this current space, and not spend too much time on the math, And
Shaknik, you only see your cover slide. Are you showing anything else?
no, I'm just showing the current slide.
Okay.
Yes. So the idea essentially is that now I will briefly go through the general timeline of how we arrived with ChatGPT. And the reason for this is very simple, is because whenever I go to these talks and they explain AI as a black box model that is meant for a general, STEM audience. So if you are an audience from science, technology, engineering, and math, and if you're going to this general talk, they usually sort of try to black box these AI models as simply stating that, oh, they are based on sort of a probabilistic prediction model, right? And that is true, right? So everything is at the end of the day just based on probability. But there is a very fine line between trying to not give too much detail, a lot of the math detail, but at the same time not really overly simplifying it, because then you tend to lose a lot of context. So why is context very important? So even just, I remember just, I think 3 or 4 days ago, I was looking at this Reddit post, and this Reddit post was from the group ChatGPT Pro. So ChatGPT, right? You have the free model, then you have the paid subscription model. So there is one that is $20 per month here in the US. That's a general purpose one. And then you have the upper tier one, which is $200, and which OpenAI claims is their PhD mode model, right? So this specific person on Reddit was complaining that they had uploaded their so they had this CSV file of their clients, and they wanted to get some information from that CSV file. So they uploaded it to ChatGPT Pro, and ChatGPT Pro said, "Yes, don't worry, give me some time to process, and I will get back to you." So then this person is complaining, "I waited the 2 3 days, I didn't hear back. So what happened?" So unfortunately, this person did not realize that ChatGPT does not really work like that, where it's going through this, where it stops talking with you and it's supposed to be thinking, right? So it's all based on a direct autoregressive prediction, one token after another. And also this person should not have probably uploaded confidential CSV files to ChatGPT, because that's another thing we have to be always be worried about, is not violating these rules known as FERPA rules here in the US. That is, you just cannot upload private information, right? So for example, in my case, I oftentimes deal with these grade books of students, and some of my courses, they have up to 250 students, right? So I might be tempted to tell ChatGPT, hey, here's my file, please extract some useful statistics, because I'm too lazy to go over the spreadsheets, right? Like on Microsoft Excel. So I should not do that, and I cannot do that because that violates the FERPA rules, right? So these are things that have to be part of your context when you're dealing with these large language models. And you should not just treat them as a magical black box, especially in engineering. So what can be the topics, or rather the pitfalls that happen? Sorry, just got a call here. Just a sec. Sorry. Right. So yeah, getting back to where I was. Uh, So the main story is that we need to get some more context in the background history. So let me just first talk about how we got to where we are. So the current search for these large language models actually began with the idea of sequence-to-sequence modeling in machine translation. So sequence-to-sequence modeling, oh, I'm getting a bad call. Just give me a sec, please. Yes, sorry about that. So coming back to the discussion, so sequence-to-sequence modeling is an example of where you use machine translation, right? And it has been there for a long time, and for the longest time, they're using more general statistical machine modeling. But the specific type of modeling that came to the scene around the era of 2014 and 2016 was what is known as the recurrent neural networks. So the recurrent neural networks, they were based on this idea of having an encoder side and a decoder side. So the idea in an encoder network is that, let's say you're trying to do a machine translation. Let's say you're trying to translate from German to, or rather, you're trying to translate from English to German, right? So then the input sequence, you're trying to compress it into a very specific fixed size context vector. So as an example here, so imagine if I have this English statement of, how are you, right? And I want to find out what's the corresponding text in German. So the idea is that each individual token in this string, so how are and you, right? So you feed them through this embedding space where the idea is that each token, it has its own unique embedding space of numbers. And this vector essentially, right? The larger it is, the better representation. So typically these vectors can be maybe 256 dimensions or 512 dimensions. So these are very typical standard sizes. So each of these tokens, right, they have their corresponding 256 dimensional vector representation. So you convert all these tokens into those numerical dimensions, and then you start feeding them sequentially to one specific cell in the neural network. So the recurrent neural networks were a time step series, right? So that means that you have the same physical encoder cell. And the idea is that if you had, let's say, 4 tokens, as in this slide, then you would sequentially feed each token. And then with each time step, the underlying math within this cell, right? It would gradually build up the context of your input translation. So let's say if you have 4 tokens, you would iterate over 4 time steps. And then by the end of this time step, you would basically get here the result is a context vector. So this context vector, which is again like a 512 dimensional vector, it was supposed to contain the context of your entire uh, original English text. So this final input you now feed into your decoder stack. So now you're decoding this context into your output target language, which would be German in this case. So the idea right now is at this point of time, you begin with this unique token known as start of sentence or um, the beginning of the file. And the idea is that given the context that you have obtained so far, and the fact that you're supposed to decode to German, you predict what comes next. So let's say this start of sentence special token, it predicted the current first token will be we, this token we in German, right? So then this token now gets fed back to the decoder unit along with the continuing context from the previous chain. And this continues for the successive time steps as well. So you keep generating the future tokens until perhaps, so there are 2 ways to stop this algorithm until you either hit a special end of sequence token indicating that, yes, we have completed this translation. Or maybe you can just say that, you know what, do not exceed total context of, or maybe 100 tokens, right? So this, in a nutshell, is the idea of the recurrent neural network. And the key idea was that it was meant to encode all the meaning into one final hidden state. So on the encoder side, you encode everything sequentially into this final encoder vector here, and then you feed that in the decoder stack. So the main advantage of this idea was that it was very popular to and very easy to implement, right? It was hardware complexity was not that much. But then there are also some problems with it. So the main problems with it was that the longer your input sequence became, the worse it degraded your performance because your encoder pretty much forgot the earlier tokens in the final context in the final context vector to the decoder. So this problem is known as information bottleneck. So pretty much the idea is that, if you feed it too much information, there is a cutoff to how much actually gets passed on to the decoder. And the main reason here was just because you were doing a sequential iteration of the context development. And also the other problem was that this final input that you're feeding the decoder, right? It was fixed length, and it basically was causing what is known as a semantic compression. That is, a lot of fine-grained detail was getting lost in the translation. There are also some problems of vanishing gradients that happen during backpropagation. And because the idea was that, during this time, everything was sequential with these neural networks, right? So there was no parallelism. So if you keep on doing a backpropagation over multiple iterations, these gradients that you're trying to sort of refine for your internal weights, they become very, very tiny to the point of becoming pretty much zero. So like nothing gained at all, right? And the main problem final was that this output generation was heavily dependent on the very last encoded hidden state. So what does that mean? So obviously for something very simple like how are you? That's very straightforward. So here it should have worked fine. But imagine you're trying to perhaps feed it text of Mahabharata and you're trying to decode that into German. So that entire text of Mahabharata, uh, the only relevant information that the neural network might have picked up is that Yudhishthir went to heaven, right? And so if you think that the entire context of that novel was that Yudhishthir went to heaven, then that's not a really good um, a model, right, of the actual text. So these were very issues, like severe issues that were detected with these recurrent neural networks. And this led to a very critical question, which is, instead of having this iterative sequence of trying to build up context on all the input tokens, why not try something different? Why not have this decoder side try to look back at all encoder states at the same time, and also let the decoder decide what are the important tokens to keep for your overall context, right? So basically you let the decoder figure out by itself, like out of these trillions of tokens that you're feeding it, which ones hold more importance than the rest, right? So this led to the idea of attention, which was introduced by this paper by Badanu around 2015. And the core concept was you allow the decoder now to dynamically attend to relevant parts of your hidden state sequence, right? So this led then to this sort of breakthrough paper that pretty much brought about ChatGPT today, right? And ironically, this was done not by OpenAI but Google. So this paper is Attention is All You Need. So this paper introduced what is now known as the transformer architecture. So it's an interesting paper and it's available as open source on arXiv. So I would definitely recommend everyone try reading it. So in this context, the idea was that with this architecture, you try to eliminate that sequential problem by enabling full parallelism across all your tokens, right? It also introduced the problem of self-attention. It introduced this idea of self-attention, which was you try to capture all the dependencies between different positions in a sequence, regardless of distance, right? So that is whether in Mahabharata, whether the token arrived within the first few lines or towards the very end of the novel, it doesn't matter, right? Regardless of the distance, you should be able to prioritize the attention to different tokens. And the other good thing was it scaled much better than RNNs, both in training speed and long range modeling. And again, the key idea was that you let every token in the encoder attend to every other token at once, right? Not just the previous ones. So this design pretty much became the foundation of all current modern language models, including BERT and GPT, which we'll focus now shortly. So just to give a very quick rundown on transformer training. So let's say you're trying to train this transformer. So let's say you're trying to give the input of how are you, and your output would be this matrix here of the tokens. So as you can see in this sort of model here, you have the input, this encoder side here and the decoder side here. So these are all separate modules. And in an actual implementation, you can imagine that there are like maybe 6 to 8 such stacks of encoder modules, which then get fed to these parallel stacks of decoders, right? So, but this is a very good simplified representation of that model. So the idea is that, on the input side of the encoder, you feed the original English tokens after converting them to the input embedding space. And likewise, you have the outputs here. So the outputs, you will notice here, they're actually shifted right, which means you shift one token to the right-hand side. So if this was the original output vector, now it looks like this. So you just shifted it by one space to the right. That means here at the very top, you start with a special token of start of sentence, for example. And here on the output side, you're supposed to compare it with your original output tokens, right? So that is essentially the ground truth of your model. So the idea is that when you start the training process, you feed the input tokens here in parallel, right? And that's the key thing. So the moment you parallelize it, you can just start using all those GPUs, right, to really amp up your training and your inference process. So essentially what they do is they create these attention matrices inside of the encoders where you pretty much assign a numerical ranking of importance to each and every token within your input English text, right? So that's a lot of rich context and it's all in parallel. So then you feed it through some, normalization layers and some residual layers. Then you pass it through a feed forward. So it's a very um, a straightforward, implementation of just making your training more rich. So then at the end of the year, entire encoder training, you get the final context here. And this context is capturing all the nuances of your English input, right? So this now you pretty much pass on to your decoder side. So the decoder side, and this is where really the ingenuity of the transform paper kicked in, was that they introduced the idea of masked self-attention. So in a masked self-attention, the idea is that now when you're trying to have the German tokens uh, predict themselves, right? They're getting the entire context, as you can see from the English side. But when you start the decoding process for training, you will first see that with respect to themselves, they're only allowed to look at previous tokens in the sequence. So for example, the start of sequence token, it cannot look at any other tokens from the training set, right, in German. So it only looks at itself. So basically, the job of the start of sequence token is, given all my rich context from the English original sentence, and given that I am the start of the sequence, predict what will come after me. So let's say if this were predicted correctly, the token that was generated was the we, like that German word we. So now the idea is, okay, given the context of the entire English language, the original English text, and given the fact that the current token chain is SOS followed by V, now predict the next token after this. So similarly, you start getting this sort of beautiful autoregressive chain of tokens. So as with the recurrent neural networks, you stop either when you have run a fixed context length or maybe you have reached a special end of sequence token. So this really was a I think it's a very unique model, but at the same time, very simple, I would say, to sort of, quickly code in your Python libraries, right? And you can even try right now to encode this, let's say in a special Python library, for example, Torch, that's PyTorch. So then after this transformer revolution, right, the next key breakthrough happened with what is known as GPT, or generative pre-trained transformer. So here, the idea was that, this idea was introduced in this 2018 GPT-1 paper. And they said, look, here's this transformer model. It has encoder and decoder. Let's try something even more aggressive. So what we'll do is we'll take off the encoder side. So no more encoder, right? So we only have now decoder side. And so that means in the decoder side, we no longer have need for this cross attention from the encoder. So that's good news for us. We'll make our model now even simpler. So this actually, what you see right now is essentially the fundamental model architecture of all GPTs, or generative pre-trained transformers, right? So the idea right now is, uh, for our training, we will use the same data set for both the input and the output side. So essentially, imagine now you have all the information in the world, anything that can exist online, right? So that entire sequence of tokens, you feed it on the output emitting side here, shifted to the right by one token side, and you just start this entire training sequence chain. So this was this essentially sort of created this fully autoregressive architecture, right? So now each token predicted based on previously generated tokens, right? What is going to come after me? So the idea was that despite this very streamlined architecture, when you start increasing the depth and complexity of this model, that is, you start now adding, so here you see just one simple module, right? But now imagine you're now adding 18 or 20 layers, one after another. So this gradually gives rise to this emergent intelligent behavior in this large language model. So current research, for example, you have 6 layers in GPT-1, but by the time of GPT-4, you had 96 of these layers, right? And they trade with much progressively larger and more diverse data sets. So this basically led to this gradual emergence of reasoning zero/few shot capabilities. Became very powerful because it came from this huge scale and data and not the complexity of the design itself. So then what are the main consequences of this architectural minimalism? So the main problem was that this minimalism introduced uncertainty where models were deployed as general purpose AI tutors, right? So these GPT models, as we have seen all of us, right, they produce very fluent but incorrect explanations. And they often lack the contextual grounding without the domain-specific tuning. So let's say if you're working in civil engineering, and even within civil engineering, something very specific, right? That's part of that overall broader domain. So unless you really fine-tune it to that specific domain, it might give you a lot of incorrect results as answers. So in these contexts, they appear very convincing, these LLMs, even when they're actually pretty much factually incorrect or pedagogically misleading. So this current study is an idea to explore how these models perform in educational settings, specifically on open-ended STEM questions. So again, with respect to the motivation, so when you're trying to compare the accuracy of these different these large language models that are available, they typically you use these standardized benchmarks. So for example, MMLU and Human Eval, these are two popular benchmarks to assess LLM reliability, but they do come with a lot of limitations. And also they're very much subject to overfitting. So let's say the first version of the model, it got a 80% accuracy score. So what do? You look at the results of your test, right? And you feed that back as your training data, right? So now the next time when you're testing it on the exact same set of benchmarks, it will give you much better accuracy. But that doesn't mean anything, right? You're just sort of overfitting it to that specific benchmark test. And the other problem is when you have these sort of benchmarks and they need to be high quality, they're very much labor intensive and they may not lead to the full assessment of the LLM responses. And this can result in a lot of unwarranted confidence in the chatbot's responses. So here's a very quick example of what a benchmark looks like. So this from the MMLU, this specific benchmark is looking at college biology as a subject. And the idea is the LLM is fed these questions and it has to select from the given options, right? Like pick the correct option from these choices. So that's how you create the score for these LLMs. Now, the thing is, for most of us today, right, we use ChatGPT mainly for helping us with coding. But even in the context of coding, let's say ChatGPT does not give you the correct result. So what do? It's very easy to sort of verify. You run it on your runtime environment and you yourself see real time where the mistakes were. But the problem is when you're trying to verify LLM responses to more open-ended questions, for example, let's say in computer architecture, it becomes more difficult to verify the correctness. And it gets even more complicated when the chatbot's persuasive conversational style, it can mislead students into thinking that the responses are correct despite having inaccuracies. And I can do as someone who is when I read the homework or when I look at their lab, their lab assignments, I know exactly when they're using ChatGPT, right? It's very unique. Like the signature that it leaves behind, it's very easy to detect for instructors. And the main problem is it's not even correct. Like it would be good if their answers were actually correct, but oftentimes they are not. And also the response quality from these various chatbots. So whether you're using ChatGPT or Gemini or Llama, so they do vary significantly, and this can actually affect students' understanding based on accuracy, the persuasiveness of the responses, and the depth of explanation. So this current study aims to sort of bridge the gap between these broad assessments of the efficacy of the responses and how students in turn experience the feedback they receive from these chatbots, right? How does it shape their learning of computer science and engineering education? So that was the main motivation. Now, in terms of related work, so we did this paper a year ago. So at that time, there was extensive literature that was, talking about optimizing coding education. So people were concerned about the reliability of coding responses from these chatbots, right? But there was very limited research on how these different freely available chatbots were responding to these open-ended questions in engineering. So, and even when there was sort of these comparison tests, they were done on those previous standardized benchmarks that I mentioned earlier, like MMLU or human eval, right? There was nothing that showed you these personalized evaluations of these chatbots and how we can perhaps try to assess the reliability. So based on this idea, we thought that we should now we should explore this idea of assessing chatbots as AI tutors for these open-ended STEM questions, which require more context, and they just don't have simple right, wrong, or yes, no answers, right? So for example, again, right, if I were to tell you what is the full form of BJT, so if it's bipolar junction transistor, that's very specific. So it's a very specific yes, no, or right, wrong answer. But if it's something more nuanced, like for example, many problems in engineering, they have the trade-off situation, right? Like when you introduce an optimization, that always results in some sort of trade-off in some other area. Can these chatbots explain that nuance correctly? So we wanted to sort of explore this idea. So the proposal was that we develop these metrics to evaluate open-ended questions that we pose to these chatbots, and they will be meant to assess their performance in accuracy, persuasiveness, and depth of explanation. So these metrics were grounded in these very core theoretical frameworks in engineering education, which is the constructivist learning theory, the elaboration likelihood model, and the cognitive load theory. So in the next couple of slides, I will try to quickly sort of explain what they are in a nutshell. But the main research question that we now ask is, how do these large language model-based chatbots, for example, ChatGPT, Claude, Gemini, and Maity AI, they differ from each other in their ability to effectively explain these complex engineering concepts in terms of accuracy, persuasiveness, and depth of explanation. So the method was that for all of these chatbots, we asked the exact same open-ended question on computer architecture. And the specific chatbots we evaluated at the time were 3.5, because remember, this was around May 2024. So 4 was not yet released. So that was ChatGPT 3.5, then Claude, Gemini, and Maity AI. And also currently for this talk, I'm also running the local large language model Dolphin. So we'll look into Dolphin's responses as well. And I chose computer architecture because I've been teaching computer architecture for almost 5 years. So I thought that would give me much more familiarity in judging the LLM responses. And we also made sure that all these chatbots were freely available online. So there was no installation required or complex setups that students had to go through. And this easy accessibility ensured that it was relevant to the typical student interactions. But I want to make it even clear that although in this use case, I'm looking at computer architecture, the template should be generalizable across various engineering educational contexts and settings. So to give you again some context, right? So the key idea that we wanted to explore in computer architecture with the chatbots was the debate of risk versus CISC. So I think if you're coming from CS, this is something that's definitely going to be very, very familiar to you, right? And it's a very interesting debate. So, I don't have the bandwidth to explain the entirety of it, but I would urge everyone present to perhaps take a quick, take quick picture of that QR code and read that very small 5-minute article, which explains more depth into this issue. But the key idea was that CISC and RISC, they're two different paradigms of computer architecture design. CISC is complex instruction set computer, and RISC refers to reduced instruction set computer. So, in a nutshell, the idea of CISC is that when you're designing the architecture, this instruction set architecture for a CISC machine, you should have a low instruction count in the code at the cost of more complex hardware design. So the way we try to sort of describe CISC philosophy is that if you're an assembly programmer for CISC, you're going to have a very nice time, but your hardware complexity means that your silicon designer will not like you. The hardware complexity really ramps up. So CISC was very popular in the 1980s. So ISS, for example, the x86 architecture, that's CISC, right? So this CISC design was very popular in the 1980s because most commercial programming was done in assembly and compilers were not really well designed at that point, right? And but then starting towards the mid 90s and continuing towards today, right? We had the emergence of the RISC philosophy. So architectures, for example, ARM, that's RISC. And the core idea of RISC is that you have a higher instruction count in code, and this allows for simpler hardware design. So RISC design was preferred in computer architecture courses in universities because it's simpler to explain to undergrads and help them grasp foundational hardware concepts. And it also sort of reduces the cognitive load to understanding computer architecture. So the open-ended question we asked was pretty much, so I'll quickly go through the slides. So the open-ended question that we asked all these chatbots was, how is CISC better than RISC? That's like the point-blank question we asked it. And the idea was to see is whether it can capture all the nuance of the CISC versus RISC debate. So the main answer is there is no such thing as CISC is better than RISC or vice versa, right? It depends very much on the context of where you're coming from. So legacy architectures like x86, they're CISC, and we continue to see CISC because they're part of the the technology stack, right? It's very difficult now to suddenly sort of move away from x86 to RISC-V, for example, which is an example of the RISC architecture. But at the same time, RISC-V, which is an example of a RISC architecture, it's open source. So that means there are no licensing fees. You can easily develop your full technology stack from hardware to software on RISC-V for a very lower sum, right? So for example, in India, there's a very huge emergence in RISC-V ecosystem for this specific reason. So we wanted to see whether all these chatbots could capture that nuance. So the evaluation metrics we chose again were these three metrics of accuracy, persuasiveness, and depth of explanation. So accuracy simply meant, okay, of all the number of bullet points the chatbot generated, how many of them are accurate? That's pretty much straightforward. Persuasiveness was, okay, if the chatbot generates incorrect responses, how many of them were sort of explained in a very persuasive manner? Because remember, these chatbots are very good with the English language, right? So they can just directly convince you that their incorrect response is actually correct. So you wanted to study at that as well. And so we also look at depth of explanation. That is, for a given bullet point, assuming it is correct, how well does ChatGPT or other chatbots explain it with depth? So we went through some of these these chatbots, and I will just talk about a few of them. So with Gemini, that was a very low performer. So out of 7 statements reviewed, 2 were identified as incorrect. And for example, the first incorrect statement was risk tends to dominate the modern landscape. Now that's not exactly true. There is recent media coverage of RISC-V, but that still does not mean that RISC-V is dominant. CISC architectures still hold a significant presence, right? And the second misleading statement claimed that CISC is potentially faster for legacy code, but there was no further context given to this statement. So the overall accuracy was rated as 71%. For that persuasiveness and depth of explanation, we used this subjective score. So 1 is not persuasive and 5 is highly persuasive. So in this case, we gave it a rating of 1 because when it was generating the incorrect responses, it was not really being very persuasive. Like even as a student, you could guess that it was not correct. And also Gemini was offering a very brief summary, lacking in-depth explanation. And also with respect to the depth of explanation, it failed to address the complexities of CISC versus RISC from a student's perspective. So we even gave it a low score of 1. So similarly, we went through Claude as well. I'll just very briefly go over some of the key points we observed. So for example, one outright inaccuracy that Claude mentioned was that CISC decoding is simpler than RISC. This is absolutely false, right? If anything, the RISC was created to alleviate the problem of the complex CISC decoding, right? So this is completely false. And another glaring inaccuracy it mentioned was that CISC can execute some instructions in one clock cycle. That is not the case at all. If anything, it's RISC that can do some of these instructions in one clock cycle. So with respect to depth of explanation, it provided a more nuanced overview of both CISC and RISC, much better than Gemini, but it still left a lot of room for improvement. And with respect to the persuasiveness of incorrect claims, it was easier to spot. So if you're a student, you could say, you know what, Claude is not giving me the correct answer. So we observed that sort of result from Claude. So I want to just briefly touch upon this context of running OLAMA and using it to sort of look at the results of this local large language model Dolphin. So it's been 1 year since we published this paper, and over that 1 year, you can now run actually a lot of these large language models locally through very minimal hardware setup. So there is one framework known as OLAMA. So using OLAMA, you can even run 4 gigabyte or 8 gigabyte sized models locally on your machine, and they give pretty good results. So we chose Dolphin as a point of reference. So we ran Dolphin also because if you have a local LLM, you can now have more privacy. So your results will not be shared with OpenAI or Google or Facebook, right? They remain with you. And we wanted to see how Dolphin now compares with these more general large language, these commercial large language models. So it was not really bad. Accuracy was 666%. Depth of explanation was 3 out of 5. Persuasiveness was 4 out of 5. And here's a general sort of table for all the chatbots we looked at, right? And as you can see, 3.5 was pretty good. Even a year ago, 3.5 was really good across all the metrics. Gemini was not that good within the commercial ones. Dolphin accuracy, as you can see, is not that high, but it comes with a twist, as I will explain shortly afterwards. So this entire study, as you can see, it was fully subjective, right? So only accuracy, as you can say, is an objective measure, but persuasiveness and overall depth of explanation, they can depend from whoever is assessing the LLMs, right? So that is one study limitation that we addressed in this slide. So I will not try to go over all of it because of the lack of time. But just to give you an idea, so to give some sort of comparative test where we have more quantifiable metrics, we chose the more old-fashioned precision, recall, and F1 scores in machine learning. So when we look at the results from the point of view of precision, recall, and F1, so precision essentially is the percentage of the chatbot claims that are actually correct. Recall is the key ideas, the fraction of key ideas that the chatbot remembered to say. And F1 is a balance between the two. So we know that ideally for any model, we want both high precision, high recall, and F1 should be comfortably somewhere near the value of 1. So in this case, again, as you can see from this perspective, ChatGPT 3.5 was the all-rounder winner, right? It was a clear winner. But also remember 3.5, I was using the paid model. This was not the freely available version. But the freely available versions, they were all over the place slightly. But note that here in this context, Dolphin, as a locally run language model, barely 8 gigabytes in memory. And you can even run Dolphin right now on your local CPU. It's not really that much power intensive. So it was giving a pretty good result in this context of precision, recall, and F1. So this evaluation still matters because most students still use free chatbots, and even though we used it on ChatGPT 3.5 back then, today ChatGPT 4 it still downgrades to 3.5, the free version after the chat limit has crossed, and um, and even though the ChatGPT Pro, so ChatGPT Pro by now is pretty fairly good, but it's still behind a paywall, and students they do not like to pay. So I know that all students that use ChatGPT in my case, pretty much most of them they do not go for the paid version, right? They use the free version. And also we are also many universities now exploring locally run AI tutors for privacy concerns and also to keep the models weight simple. So when you're running these LLMs locally, even then we should be concerned about how accurate they are for their responses. Because whatever happens at the end of the day, we do not want to give wrong, we do not want to have these tutors confidently giving wrong responses to the students. And we want to ensure that any hallucinations, they are avoided. So the future work is we continue to sort of try to recruit students. So my key plan right now is try to have more comprehensive study where I will, have student researchers try to replicate the student across multiple chatbots with different variations of the question so that we have more generalizability of the findings. And then we can ultimately come with a more solid rubric and evaluation system for these instructors. So with that, I will try to conclude my talk because I think I went a couple of minutes overboard. So again, thank you everyone for your attention, and I'm now open to some questions.
Thank you, Dr. Nath, for the wonderful presentation. Now, given some of the question
Mhm. Oh, I think yes,
from
see some of the comments. So to answer Somnath's question, yes, vanishing problems, exploding problems were you solved using the LSTM problem, but the transformer solves that even more aggressively. So for example, with residuals, right, you could not really implement that in RNN. So yes, I should have mentioned that, but I was short on time. So we did have some
Sagnik, I just had a comment here. Before you take any question, please repeat the question because when it will be recorded, recording will be watched. They need to also know the question.
Oh, sure. So no, I just saw one quick question in the chat from Sona saying that the vanishing exploding problem was solved using the LSTM before the transformer architecture. So that is true, but the transformer does it even better, is essentially what I'm trying to say, because it has the parallelism to help it, and also with the idea of doing the residuals. So that is an important point, and I think I should have probably added that context in my talk as well. So thank you for that. So yes, so I can quickly answer some questions in the chat as well. So yes.
next
So
one question from Hassan Sikda.
uh-huh.
What do teachers and professors do to help students aware of these AIs to help them understand and how to use them in their study?
So the long or rather the short answer is that it's a very mixed like a mixed responses, right? So some faculty they still are very much anti-AI, they do not want it. Some faculty do, they encourage it. So many universities across the years they now have these specific sort of policies that have now created with respect to sort of using AI in your material. So some courses they will say no, do not use any AI. Some will say if you're using AI, you must mention it, because if for whatever reason we run your code through a evaluator, some sort of autograder, and it responds that is likely 90% AI, you might be called into questioning, and if you are not honest, you might get penalized. So that's like been the typical policy. in my case, for example, I tell them if you are using AI, just make sure that you use your own intuition to make sure that the responses make sense. Right? It's not just complete garbage. So I think there's another question from Somnath. Will this AI tutors be useful for subjects like mathematics, philosophy, which is heavily logic based, not information based? So I think it depends. I think for math, I think if you create the benchmarks where there's specific yes or no answer, I think it's feasible. But again, right, if it's more nuanced, for example, philosophy, I don't know, right? I mean, and that is where I think the current study, you can easily sort of generalize that to this area as well. Is how do you get more nuance? Like what kind of metrics can you make? Because obviously, if you're trying to have a philosophy professor create those rubrics, they will not be able to relate to precision F1 and recall, right? They will try to look for something that's more portable to their specific domain. So that's a very interesting question. And to be honest, I would say I think there is no clear-cut answer on that. Any other questions?
If anyone have any question, you can.
Okay, I think we can go to
Okay.
Professor Maity.
Thank you, everyone.
Okay, so moving ahead, let me introduce today's special guest, Professor Santi Maity. Dr. Maity is a professor in the Department of Information Technology at IIST Shibpur. With over 26 years of experience in teaching and research, he has made major contributions in areas like cognitive radio networks, medical image analysis, digital watermarking, and reinforcement learning. He has published more than 310 research papers in top international journals and conferences, and his work is recognized both nationally and globally. So we would now like to invite Professor Maity to say a few words about his department and share some thoughts on the today's session in AI in computer science and engineering education. So over to you, Dr. Maity.
Thank you, Debojit. Am I audible?
Yes,
Can
you
you
are
hear
audible.
me? Yeah. Thank you,
Yes.
Debojit, for introduction. Thanks, Shah sir and GAABESU for such an academic initiative. Thanks to Dr. Sagnik Nath for his wonderful, nice lecture. As part of IIEST on the fields of AIML research, teaching and academic other activities, I just like to briefly say that even late started, but in recent past and now the many faculty members of diverse disciplines are actively engaged in the research. I just briefly say, for example, civil engineering and architecture planning departments, they are involved in EIML for structural health monitoring, structural engineering, especially on uncertainty quantification, reliability analysis, uh, environment and geotechnology groups. They are working on hydroclimate analysis, monsoon dynamics modeling, rainfall forecasting, and energy efficient and intelligent buildings, smart building systems. Mechanical engineering, metallurgy, and materials engineering groups, faculty members are involved in AIML research on energy system modeling and optimization, including biomass-based power systems, ML in material science, material informatics, multi-scale modeling, manufacturing informatics, predictive modeling of damage in advanced composite biomaterials, and mining and earth science departments faculty members are involved in AIGIS analysis, urban planning, rock type classification, pool sample analysis, and grade prediction. And in electrical engineering community, I mean electrical, electronics, computer science, IT, School of Mechatronics, Robotics, CHAST, I mean Center for Health, and aerospace departments. They are actively involved in diverse research like robotics and control systems, power systems and generation, particularly the fault diagnosis of generation systems and transmission line problems, fault detections in electrical machine, particularly in induction motors, and VLSI or sensor research groups. They are working on ANN-based biosensor, resource-efficient VLSI architecture, analog circuit testing using on AI/ML. And in healthcare science, there are different departments. Faculty members are actively involved in research like medical imaging and analysis, biomedical and bioinformatics, genomic research, cancer diagnostics. A large number of, I mean, good number of faculty members involved in computer vision and image processing are working on applications like food and agriculture, particularly the crop or plant disease detection, cyber security on facial emotion recognition, robust deepfake detections, generative AI model for hyper-realistic media synthesis and detection. Faculty members are also working on wireless communication, sensor networks, and IoT involving AI/ML, intelligent transport systems, particularly traffic forecasting, traffic speed prediction, charging station deployment, road network generation, and computer science and IT faculty are involved in natural language processing and social networking, machine-based translation, social network analysis, fake news article detections, and mathematics and computer science departments are involved in neural networks on nonlinear dynamics, ecological modeling for handling uncertainty and supports multi-criteria decision making, applications of AI/ML to simulate biological systems, disease prognosis using neural networks and nonlinear analysis. In fact, a good number of sponsored projects from DST, ACRB, DBT, IIT Kharagpur, AI4 hubs. The projects are being ongoing. Involved, I mean, the different faculty members are working on these funded or sponsored projects. In recent past, there were conferences on related areas of AI/MLs like International Conference on Intelligent Systems and Security in the last December, I mean 26 to 22nd December 2024, and in first international symposiums on artificial intelligence and Internet of Things in January 1st and 2nd 2025. And those shortage of faculty members, but due to ongoing faculty recruitment, hopefully the computer science and IT department will start intake program in machine intelligence and artificial intelligence separately. And with the new course of NEP 2020 programs, there is in the course curriculum the first year course that introduction to AI/ML for all engineering departments. Apart from that, application of AI/ML in other engineering departments are also being introduced. So I hope there would be a positive collaboration initiatives from GAABESU with the faculty members of IIESTShibpur in terms of funding sponsored research projects and academic and industrial research project collaborations. And also we are looking for developing an AI/ML center for research. So if there is any initiative from the GAABESU in terms of fundings or in establishing such AI/ML center, it would be nice. Once again, I thanks Dr. Sagnik Nath for it's really a very timely, relevant talk, and it's very pertinent for the teaching, learning, and engineering teaching learning process. It's I think it should be very useful for the faculty community who listen these talks and how to make use of this effectively in teaching learning process. Once again, thanks GAABESU for initiative. Thanks Debojit for conducting these programs. Thank you.
Okay, thank you very much, Dr. Maity, for sharing valuable insight. And thank you, Dr. Nath, for the insightful and inspiring session. We are almost out of time, so we'll have to bring the session to a close. A big thank you to all the participants for joining us today. Special thanks to Professor Santi Maity for his patience and kind words, and to the computer science and data science SIG leads for organizing this wonderful session. With that, we conclude today's session. Thank you once again and have a great day ahead. Thank you.
Thank you.